Okay, so this begins part 2 of lesson 8 for rational functions. So let's think about what we mean when we say the zeros of a function. So when we think about the zeros of a function, like when we thought about the zeros of a quadratic function, I'll just do a quick sketch of a quadratic function. So say we had this quadratic function, and there's a parabola which represents a quadratic function. We know that when we said the zeros, we actually meant these points right here on the x-axis where the graph crosses. And so what is a zero? Well, it's the value of the x that makes a function equal to 0, that makes the output 0. So it's the value of x, which is also called the independent variable, that makes the function so in other words, when the output is 0, the x-coordinate that is associated with that would be the 0. And what that means graphically is that means the x-intercept. So we see that that's the point where the graph crosses that x-axis. And what has to be true about a fraction to make it 0? That's another thing that's associated with what we're going to be talking about next. If you think about if you wanted a fraction to be equal to 0, you can't have a 0 on the denominator because you can't divide by 0, but it would require the numerator to be equal to 0. Because 0 divided by anything except for 0 would be 0. So keeping kind of all that in mind, we're going to be taking a look at how we can find the zeros of some rational functions. So in this example, example 3, we're going to be looking at some functions that are definitely more complex than the ones we just looked at prior to this. But we're not going to be actually trying to describe the transformations that are going on here. Because you're looking at example A, x squared plus 3x minus 4 over x plus 3. Well, in the prior examples we just looked at, our numerator was always just a constant value, like a coefficient. And here there's x's and all that. So we're really going to focus on other parts of rational functions in this portion of the lesson. And the first thing we're going to do is take a look at what would be the zeros of these functions. Well, what we just said is in order for a fraction, which is what this is, to be 0, the numerator would have to equal 0. So when we want to find a 0, we just focus on the numerator. And we want to see what values would make that numerator equal to 0. We know that if we looked at the denominator and saw what makes the denominator 0, that tells us where the graph's undefined. And that would actually tell us stuff about the asymptotes. But if we look at the numerator, it's telling us the x-intercepts, or the values, or the value of x that would make the function's output 0. So, and I see x squared plus 3x minus 4. It's not directly apparent what values would make that 0. So I want to think about factoring that, because I can tell by looking at the binomial factors much easier than looking at it in expanded form. So I think about x squared plus 3x minus 4. If I factor that, both of my binomials will have to start off with x, and I need two numbers that multiply to -4 that add to +3. So right away I thought of +4 and -1. Because 4 times -1 is -4, and 4 plus -1 is +3. So now if I looked at that numerator, I know that if I set x plus 4 equal to 0, I know that x would have to be -4. So that's one of my zeros. And if I set x minus 1 equal to 0, I have to add 1. So that makes x equals 1 as one of my zeros. Sometimes you'll see them written as ordered pairs. So if you were going to write them as ordered pairs, you could write them like this. You'd have -4, 0, and 1, 0. So again, the denominator has a purpose, and especially when we're kind of thinking about actually graphing these. But for now, we're just focusing on the zeros. And so we only need to look at the numerator to do that. So I want to go ahead and designate B as a you try question. So I'm going to have you give that one a shot and then tune back in once you've found the zeros of this function in example B. Please pause the video now and find the zeros. Okay, so the zeros of example B are -6 and -1, or if they're written as ordered pairs, -6, 0 and -1, 0. All right, let's go ahead and turn the page. Okay, so we started off part 2 talking about the zeros of a function. What our goal is for this part of the lesson is really just to kind of come up with all the things and talk about all the parts that are that affect the graphs of these rational functions. And so we talked about the zeros, and we know that means where a graph crosses the x-axis, and we talked about how to find those, looking at the numerator and finding what makes it zero. And now we're going to look at asymptotes. So we've already kind of seen some, some talk about we've done something about the asymptotes for those other more basic functions. But in general, if we wanted to talk about vertical asymptotes, so the vertical asymptotes, which are written in the form of x equals some real number, they are actually found by factoring the denominator. So that's what that denominator is telling us. It tells us the value of x that would make it undefined, and since the equations of vertical lines are x equals, if we find the value where x would be undefined, that actually is where the vertical asymptote would lie. Now horizontal asymptotes, they're always written as y equals some real number. And with these more complex kinds of rational functions, how we find a horizontal asymptote is actually by looking at the degree of the numerator and comparing it to the degree of the denominator. And this chart here details how if you compare the degree, which remember that means the highest power on any of the terms, if you were to compare them, this chart tells you about the horizontal asymptotes. And what it tells you is this: if the degree of the numerator is greater than the degree of the denominator, so in this case here, okay, so that first row is telling us about how the degree of the numerator and the denominator compare. So if numerator's degree is higher than denominator's degree, then there will be no horizontal asymptote at all. If the degree of the numerator is less than the degree of the denominator, which actually was in the case of those ones where there was a constant term on top because it was degree 0, and then we had a variable x on the bottom, that was the case, the degree of the denominator was greater, then that's why we had a horizontal asymptote at y equals 0, which is the x-axis. Now if the two degrees are the same, so if they have the same power, like say we have a degree 2 on the top and a degree 2 on the bottom, if they're equal, then we can actually use the this little formula here to find out what the horizontal asymptote would be. We'd take the leading coefficient of the numerator, okay, so that means the number in front of the highest power, and divide it by the leading coefficient of the denominator. And that ratio between those, the equation y equals that ratio, will be the equation for the horizontal asymptote. So that's a little bit to take in. So let's go ahead and see if we can look at a few examples and put it into practice. It might make it a little easier. So this next example says identify both the vertical and the horizontal asymptotes of the function. So we're going to be looking at a vertical and a horizontal asymptote in both cases. We know that vertical asymptotes, vertical lines are always in the form of x equals, and horizontal ones are always in the form of y equals. So we'll at least get that started. So, okay, so vertical asymptote, we said, right up top of this page, we said you can tell the vertical asymptotes by looking at the denominator and seeing what makes it equal to 0. In other words, find the places where the function's undefined. So if we look at this denominator here, and we talk about that vertical asymptote, the only value that is going to make that denominator equal to 0 is 0 itself. So my vertical asymptote is x equals 0. Now what about the horizontal, or is there a horizontal one? So when we look at the degree on the numerator's degree is right here, it's 2. And the denominator's degree, it's x to the first, so its degree is 1. So we know that we have a situation where the n is greater than the d. And if you look right up here, when n is greater than d, there is no horizontal asymptote. So we just cross this right out and we say there's none. There is not a horizontal asymptote for this particular graph. All right, how about example B? So vertical asymptotes and horizontal asymptote. So the vertical asymptote, we're going to be looking at the denominator. We're going to look to see what would make it 0. So I know that I could factor that denominator down to x minus 1 and x plus 1 because it's a difference of squares. And so I actually know that this actually has two vertical asymptotes. It's going to have one when x equals 1 and when x equals negative 1. So it's going to actually have two boundaries vertically. X equals 1 and x equals negative 1. Okay, so what about the horizontal asymptote? We have to look at the degree of the numerator. Well, the degree of the numerator is 1 because it's x minus 2, so the highest power is 1. The degree of the denominator is 2, and so we have a situation where we know that n is less than d. And so we'd have to look at this part of the table. If n is less than d, then we know that we must have a horizontal asymptote at y equals 0, which is right there at the x-axis. Now notice we haven't done too much with the numerators other than just looking at the degree. If this question had also asked us to identify the zeros of each of these functions, then we would have to look at what makes the numerator equal to 0. But we'll kind of put it all together eventually. Right now, we just want to know this is how we find the asymptotes. How we would find the zeros is we'd actually see, like for instance, if I went over here to this example and I looked at the numerator, I could find the zeros. I could say, all right, well, I'm going to factor that numerator. X minus 4 and x plus 1 would be the factored form, and that means I know the zeros are at 4 and negative 1. So, but again, they didn't ask for that in this case, but these would be where the zeros are. So every piece of the function has its role and tells us something about the graph. It's just in these questions we're focusing specifically on the asymptotes. Okay, so normally I would want to make this one a you-try question, but because there's a third scenario that happens with the horizontal asymptotes and that happens in this question, we're going to go ahead and do this one together. Okay, so vertical asymptotes. So when I think about the vertical asymptotes, I have to look at the denominator, and I want to see what makes it 0. Well, factored form of the denominator would be x minus 3, x plus 3, and so again, I'm going to have two vertical asymptotes. I'm going to have one at x is equal to 3 and one at x equals negative 3. So two vertical asymptotes here. And now what about horizontal? Well, so to do the asymptotes horizontally, I have to compare. So I'm going to get the degree of the numerator, and the degree of the numerator is 2. See, its highest power is 2, and the degree of the denominator is also 2. And so the situation actually is found in the table right here. So when they're equal, what we have to do to find the horizontal asymptote is we will take and write this equation, y equals, and it's going to be the ratio between the leading coefficient on both. So the leading coefficient of the top is 3, the leading coefficient of the bottom is 1, so that's actually going to be 3 over 1, or just 3. So that's going to be the equation for my horizontal asymptote. It's going to be y is equal to 3. So that means basically this graph must have been shifted up 3 units because normally the asymptote would be right there on the x-axis. So that's the 3 different scenarios that you could see occur with horizontal asymptotes. But vertical asymptotes always come from looking at the denominator. And I think we've done one of each, so we'll just go ahead and skip example D. We'll just put a little skip on that and we'll go ahead and turn the page. So we've talked about zeros of rational functions. We've talked about where the asymptotes are, how we can locate asymptotes. And now we're going to talk about a special phenomenon called holes in the graph. Well, sometimes holes occur in graphs, and here's when holes will occur in a graph. If a rational function has the same factor, x minus b, in both the numerator and denominator, then there is a hole in the graph at the point where x equals b, unless x equals b is a vertical asymptote. So what is that? Well, that kind of sounds complicated. What does that really mean? So I know that on your notes, you have a sentence with the fill-ins on it. I don't have that on my graphic here, but that sentence that's just above this table for holes actually summarizes what the table says. And what your fill-in should be is this. It should say, when a function's numerator equals 0 and the denominator equals 0, for the same x value, the graph may have a hole. So when the numerator equals 0 and the denominator equals 0 for the same x value, so let's take a look at seeing if we can find if graphs have holes, and if so, identify where they are. Well, in this first example here, I've graphed x minus 2 over x squared plus 3x minus 10 for you. And when I look at the graph, I don't see any holes, but that doesn't mean there's not any there. When you graph using your graphing calculator, the hole is located so exactly because it's at an exact point, and because of the resolution of your calculator, you really cannot see on the graph itself a hole. You actually will be able to locate it in the table, and when we're together in class and we kind of talk about the use of the calculator, I'll show you how you can tell in the table. But for now, if we want to know if there's a hole and find out where it is, what we want to do is use this sentence that we just filled in. When a function's numerator equals 0 and its denominator equals 0 for the same x value, the graph may have a hole. And so the first thing we want to do to be able to tell when the numerator and the denominator have the same 0 value is we want to first see if we can factor and cancel out anything. Those things that will cancel out, that indicates that there's the same thing on the top and the bottom. And since we know how to tell what makes a binomial equal to 0, if those are the same binomials, then they would have to have the same zeros. And so if those cancel out, they're going to cause a hole. So the numerator here is x minus 2. And if we factor the denominator, it factors down to x. It's going to be a plus 5 and a minus 2. 5 times negative 2 would be negative 10. 5 plus negative 2 is positive 3. And so now you can see what happens is this x minus 2, that cancels out. And that leaves me with just the function 1 over x plus 5. And that's why this graph actually looks like that basic parabola with the graph translated to the left 5. And you can actually see, drawing it in, where that asymptote occurred at x equals negative 5 because there was that horizontal shift. So that made that vertical asymptote there. So it looks exactly like the graph of 1 over x plus 5 because the x minus 2's on the top and bottom canceled out. Well, they still had an impact on this graph because the one difference between that and the graph of 1 over x plus 5 is that there's a hole now when x equals 2. So the hole is at x equals 2, and that means right here where the value of x is 2. So there's actually a little hole right there, and maybe to be represented a little better, I should actually put a hole there, like a little open dot. So there's a hole right there on the graph. So we can tell by factoring and seeing what things cancel out, and the value that would make the pieces that cancel out equal to 0 is where the hole is located. Now the 0 on the denominator that remains causes that asymptote that you see at x equals negative 5. Let's look at the next example. So in this one, there actually is not a hole, and here's how we can tell. So if we look at f of x is equal to x minus 2 over x squared minus 4x plus 4, and we factored it. So we know that the numerator is already factored, x minus 2. We take the denominator and we factor, and when we factor, our two binomial factors are going to both be x minus 2 because negative 2 times negative 2 is positive 4, so we need that last term to be positive 4, but negative 2 plus negative 2 is negative 4 in the middle. So then what happens is, when I cancel out this x minus 2 with the x minus 2, we'd normally think, well, that means there must be a hole there, but we still have an x minus 2 left on the bottom, and that one that's left over actually means that's where the asymptote is. So the hole in the graph actually occurs on the asymptote, and so the graph itself doesn't really have a hole in it. And that new asymptote is actually at, or the asymptote is actually at x equals 2, and you can actually see that on the graph. This was just shifted, because this turns out that this looks just like the graph of 1 over x minus 2. And that asymptote occurs on, or the hole occurs on the asymptote. So that is a situation where there's not a hole because we canceled out an x minus 2 on the bottom, but there was still another one that caused that asymptote there. Let's take a quick look at a couple more examples. So it says identify the holes in the graph of f of x and then graph it. So again, we want to start off by factoring. And so if we factor the top, I have an x minus 3 and an x plus 3. That's a difference of squares pattern. On the bottom, I have an x minus 3. Okay, well, so in this case, when I do my canceling, I do see a common factor. I don't even have a denominator anymore. Well, actually, I do have one. It's 1. So this just leaves me with x plus 3 over 1, or just f of x is equal to x plus 3. Well, so this actually, the remaining function, x plus 3, that's a linear graph. So if I wanted to graph what this looks like, I would be graphing a line, but there is a hole. And there's a hole that's going to occur at x equals 3. So I want to start off and graph the function. So when we graph a line, we know that we graph the y-intercept, and then we rise and run according to the slope. And the slope is just 1, right? So we could plot the point, which is the y-intercept, that's at 3 here. And then we're going to rise 1 and run 1. So rise 1, run 1, rise 1, run 1. I could go down 1 and left 1. And so I get this line. So I'm kind of drawing this line like it's just a normal linear graph. But clearly, if we look at that original function, that's not a linear graph. So, I mean, it's not just, it's not exactly as it appears when you write x plus 3. There was more things that went on in the original function. And so what happened is there was a hole created at 3. And so it's like right here, where x equals 3, right there, there's actually a hole. So I'd want to leave a spot right there in my graph where I maybe just put a little open dot, and then that's where my hole occurred, is at x equals 3. It's like right here, where x was 3, it was kind of like there was an asymptote in just one specific spot. So it just kind of took off that point. That it doesn't exist in that point, but it exists every other place, and so it created that hole. Also, something that's kind of important to note is notice this graph comes down here and it crosses right there on the x-axis at -3. Well, that value right there is what would make that numerator equal to 0. And remember, the numerator tells you the zeros are the x-intercepts of the function. So we can kind of see that clearly on the graph. All right, let's look at the final example. So again, we want to do some factoring first to see if we can figure out if there's some things that will cancel or not. And if not, then we'd have to graph that whole thing. So the numerator, I can factor using the easy method. I need factors of -6 that add to +1. And so that means that I'm going to have to use a +3 and a -2. Well, that works out great because there's an x minus 2 on the bottom, so I can cancel those whole quantities, and that's leaving me with, again, the same graph. This looks exactly the same as the last one, except that the hole is in a different spot. The hole this time is going to be at x equals 2, because that's what would make this part equal to 0, those two parts equal to 0. So again, I can graph it using slope y-intercept form. So I'm going to have a y-intercept at 3, and I'm going to have a slope of 1, so I'm going to rise 1, run 1, and these points are going to just be formed by rising and running 1, or going down 1 and left 1. And so when I graph the line, it looks like this, except for, so what I usually do is graph the line, then I go back and put the hole in. I know the hole had to occur right here at right in there where x is 2. So I just got to go in here and erase that point, and I'm going to put an open dot on my graph, and I can just label that as the hole. So that does it for today's lesson, and so hopefully we're going to be able to take all this information that we talked about with asymptotes and zeros and transformations of graphs and holes, and see if we can put these all together and do some graphs of these rational functions. Thanks for coming to class.